In Chapter 1, we looked at some conventions for making measurements, some fundamentals of working with numbers, but now we're ready to get into real chemistry, which means working with atoms, molecules, and ions. On this cover slide, I'm showing you some things that can react together. The reaction is very vigorous, and I wouldn't want to do it for you even if I could. However, I'm going to put a link to a YouTube video of the reaction between sodium and chlorine to make sodium chloride. Watch for that on your Moodle page. What I want to use this picture for is to make sure we get used to looking at the microscopic particles, looking at the particulate nature of matter, to see whether we're dealing with atoms or molecules or ions. So in the first picture, I've got some sodium here. Let me get my pen turned on to the right color. This is sodium metal, and it's kept in oil because sodium reacts vigorously with water. Even the moisture in the air would make it react. It's kept under the surface of oil so that it won't react. Now, the formula that I see there is just sodium solid. It is a pure metal. So I'm going to pause whether you think about whether sodium is made up of atoms, molecules, or ions. I think sodium is made up of atoms. If we looked at a microscopic level, there would just be sodium after sodium after sodium after sodium after sodium atom. Now, it's going to react with chlorine gas, which is shown in this bottle with a yellowish color. Chlorine is a nonmetal on the right of the periodic table, and although I'll review this later, I hope you remember that chlorine is one of the diatomics. So I'm going to pause while you figure out whether atoms, molecules, or ions are present in the chlorine. In chlorine, the Cl2 in the formula tells you that two Cl atoms are bonded together to make a Cl2 unit, and those are molecules. Atoms covalently bonded together are molecules. And note that there's a big difference between Cl2 and two Cls. Now, when you watch the video, you'll see that they react very vigorously to make sodium chloride. And I'm going to pause while you decide whether that's made up of atoms, molecules, or ions. What I see there is a metal combined with a nonmetal in the same compound. And I'll review that later. But that's how I know that this is an ionic compound. Although I don't see the charges in the formula, this is actually made up of a network of sodium ions surrounded by chloride ions, surrounded by sodium ions, surrounded by chloride ions. Those charged particles are ions. So right in this one reaction, we see atoms combining with molecules to make ions. Of course, that's different from case to case. But let's go back to the very beginning. I told you this course would go back to the very beginning. We're going to review very quickly again what you saw in high school. We're going to look at the origins of our model of the atom. And this is a historic lesson. I am not going to have you remember who's responsible for what model of the atom and what year it was proposed. That's not my nature. When I tell you about this story, we're focusing on how a scientific model evolves over time. The first thing you'll see is that the evolution goes from thought to empirical knowledge based on the data or on experiment, and that's what science is. The other story that you'll see is that if you want your model to be accepted, it will explain previous data, but it's really powerful if you can predict an observation that hasn't been made before. Then you will get support for your model. So let's go back to the dawn of modern time, back with the ancient Greeks. The first use of the word atom is believed to have been by a man called Democritus, an ancient Greek. And this word here, I just used my Greek font on the computer. That in English letters is atomos, or an atom. Democritus thought about cutting a piece of gold in half. That was still gold. Cut it in half again, still gold. In half again, still gold. But he thought that eventually you would get a piece so small that you could not cut it in half and still have it be gold. And that smallest uncuttable part he called atomos. Now that's an inspired thought, but it doesn't count as science because science is based on data. It's based on experiment. It's empirical. So we're going to jump ahead to the first modern model of the atom proposed by John Dalton here in 1803. John Dalton presumed that an atom was an indivisible sphere. And the picture at the bottom here is an actual picture of the spheres that Dalton himself made to be his model. So he was suggesting that carbon dioxide had an atom of carbon and 2 atoms of oxygen. He said that the spheres of carbon were different from the spheres of oxygen, but all oxygen atoms were the same sphere. So all atoms of the same element were the same, atoms of different elements were different. He said that a chemical reaction was just a redistribution of those spheres. You rearrange the balls to come up with a new arrangement of balls. But because the atoms couldn't be created or destroyed, mass couldn't be created or destroyed. And that explained the law of conservation of mass. It also explained the law of constant composition. Every time you made carbon dioxide, that was 1 sphere of carbon and 2 spheres of oxygen. So just because the atom ratio was the same every time in the compound, the mass ratio related to those atoms had to be the same every time. And that explained the law of constant composition. He also explained the law of multiple proportions. Carbon and oxygen make more than 1 compound. You can make carbon dioxide, but carbon monoxide is another known compound of carbon and oxygen in which 1 atom of carbon combines with 1 atom of oxygen. Now, we don't believe this model is exactly true anymore, but we're not going to discard the model altogether. We're just going to add to it. The model on the right shows the kind of model that I might still use today. You'll see when I'm working with you in tutorial that I often use a model kit like this to make molecules, and each ball represents a different kind of atom. Even though I know the atom is more complex than that, this model has a simplicity to it, so that even when I know the situation's more complex, when I go on to more modern models, I'll probably retain this model kit with the spheres for simple cases. What was wrong with Dalton's indivisible sphere is that it presumed that the atom was the same all the way through. Technology changed though, and with a new kind of technology came new kinds of experiments, new kinds of data, which meant that we had to change the model. So Dalton proposed his model in 1803. I'll tell you that J.J. Thomson proposed his in 1897. Again, not that I want you to remember that, but we're about a century later. And the technology that Thomson was working with was with electricity. He worked with a cathode ray tube. There are pictures in your text. I hope you're reading your text. It's a lovely, rich resource, and they are better artists than I am. But let me see if I can make you a sketch of a cathode ray tube. That's just a sealed glass tube where I've got a very low pressure of gas inside. There's a metal electrode at each end that's hooked to a power supply. That's supposed to say power. And when you apply a voltage across those electrodes, what you will see is a glowing beam of light. When you hold a magnet up near that beam of light, the beam is deflected. And you physicists know that to deflect a beam in a magnetic field, the beam must be made up of charged particles. So that proved to us that the atom wasn't uniform all the way through, that there must be charged particles inside. Thomson's experiment showed that there were negatively charged particles that could be removed from the atoms and make that beam. So that beam is made up of electrons. So Dalton's model of the atom took the sphere and said, look, we've got negatively charged particles embedded in a bulk that is positive overall, so that the atom in total is neutral. But when you apply a voltage across it, you can remove the electrons from the atom. He said the electrons are embedded in the bulk of positive charge, just like the fruits embedded in a Christmas plum pudding. Now, Thomson was British. He knew what a plum pudding was. Maybe you call it a fruit cake. In America, they sometimes call it a blueberry muffin model of the atom instead of the plum pudding model of the atom, because they don't know what a plum pudding is. But if you call it a blueberry muffin model, again, you're imagining the electron blueberries embedded in a cake that's positive. So this model retains the features of Dalton's model. It still explains the laws of constant composition and conservation of mass, but in addition, it explains the behavior in the cathode ray tube. So that was in 1897. One thing you'll see now is that the model is evolving more rapidly. In 1909, only 14 years later, Ernest Rutherford was experimenting with radioactivity. And he came up with the nuclear model. Again, there's a picture in your textbook, which is better than the one that I can draw, but see if I can make a little sketch. What he had was a radioactive source here that emitted alpha particles. And alpha particles had a net positive charge on them. He directed that beam at a piece of gold foil. There's the gold foil. He put a photographic shield around it, and whenever the alpha particles went through and hit the photographic plate, it made a bright spot when he developed the photograph. What he saw is that the most bright spots were straight through. Most of the alpha particles went straight through. Some were deflected a little bit. Large majority not deflected much at all. But every once in a while, he saw a bright spot on the backside of the foil, and that's what took him by surprise. He said it was as if he had launched a torpedo at a piece of tissue paper and it bounced back at him. That led him to conclude that because like charges repel and alpha particles are positive, that there must be positive charge concentrated in the atom as well. Most of the atom is empty space, so most of the alpha particles went straight through. But with the positive core of the nucleus, if the beam got really, really close to the nucleus, because like charges repel, the positive alpha particles would bounce straight back. From the pattern on his photographic plate, he concluded that most of the atom was empty space and the positive charge was concentrated in a very, very small nucleus. What amazes me about this is, if he expected the particles to go straight through, what made him think to put the screen all the way around? And I think this is the challenge of a good researcher, to not be so biased by what you expect to see that you close the door on things you don't expect. Now, again, this is a much more complete model than the other ones, but it doesn't get rid of the other models. We still have spheres like Dalton. There are electrons in the space around the nucleus, so that maintains Thomson's idea. And as it turns out, Rutherford was actually a student of Thomson's. But it says that the positive charge is not spread out through the whole atom. It's concentrated in the center, in the nucleus. Now, we're going to stick with this model for now. This is still not the most modern model of the atom. We will see more in Chapter 6. But as I said before, although we know that there are simple models in our past, we sometimes use them when we want to explain something simple. So for the next few chapters, this model will be complex enough to explain most of what we want to see. And in the next section, we'll go on and look at the subatomic particles in Rutherford's nuclear model to get going with some more practical applications of chemistry. Time to get out of this theory. One more slide I want to show you, though. Although Ernest Rutherford was from Australia and he worked with Thomson in England, there is a Canadian connection. Rutherford worked at McGill University in Montreal, and the last time I visited in Montreal, my chemist husband and I made a pilgrimage to Rutherford Park. It's a name for Ernest Rutherford. He worked some time in Montreal, and he named a park after him. Mostly it's playing fields, but there's me, in case you forget what I look like, in Rutherford Park. In the next section, we'll meet again to talk about subatomic particles.